Okay, so we are going to talk about the oxidation and reduction reactions lab. Oxidation reduction, also known as redox, involves two different types of reactions, oxidation and reduction. An oxidation is a reaction where something loses electrons, and a reduction is a reaction where something gains electrons. There's two kind of common acronyms for doing oxidation reduction reactions. That's oil rig. Oxidation is loss, reduction is gain. And you also have Leo, the lion goes grr. Loss electrons, oxidation, gain electrons, reduction. Either of those work to help you remember where the electrons are going and what that means. So I have an example of how rust is produced here, where iron is being oxidized. It's losing its electrons and becoming iron 2+, and the oxygen and the water in the air are gaining electrons from that iron and creating OH-. You can also look at this through oxidation numbers. So the oxidation number of iron was 0, and it went to an oxidation state of 2+, and so that shows an oxidation as well. And the same goes for the oxygen and the water in that reaction, in the reduction reaction. What the substance that causes the oxidation to occur, or the substance that accepts the electrons, is known as the oxidizing agent. So here, the oxygen in the water would be the oxidizing agent. The substance that causes the reduction, or that loses the electron, is the reduction agent. So here, the iron loses its electrons and causes the reduction to occur, so it would be the reducing agent. So the reducing agent is whatever compound loses its electrons in the oxidation reaction, and the oxidizing agent is whatever gains the electrons in the reduction reaction. So we're looking at multiple types of reactions in this lab, some of which are going to be reactions in water, but also we have reactions with metals and reactions with nonmetals. So when we're reacting metals with water, they have different types of reactions based off where they are in the activity series. The activity series tells us how vigorously metals will react with water or with other metals. And they're basically in order from most reactive to least reactive. Most likely to oxidize, least likely to oxidize. You can have this as metals, which I have here as my longer column, but there's also an activity series for nonmetals as well, which you'll find useful when you react your nonmetals with nonmetals in the halogens part of this lab. The overarching theme of an activity series and doing redox reactions is the more active the metal, the more it wants to exist as an ion. It wants to give away its electrons as much as it possibly can, depending on its reactivity. So you have elements up here like potassium, sodium, calcium that want to give away its electrons. It's more stable without the electrons. So it wants to exist as an ion, and it wants to oxidize to its ion and give away its electrons. Compounds lower on the activity series like mercury, silver, and gold, those don't oxidize as easily. They're more stable with more electrons, so they're least likely to oxidize, and they'd rather be in their elemental state than as an ion. Okay? So that's where we get into our reactions with water. Our most active types of metals will be able to displace or react with water and produce hydrogen gas in just room temperature water. Nothing needs to be done to that water. If it has contact with water, it will oxidize. So that's our most reactive metals, which are at the top of our activity series. Our lesser active metals will be able to displace hydrogen gas when the water is now heated. It needs a little bit of extra energy through heat in order to cause the reaction to happen. So those are our metals that are more likely in this region of the activity series. Our more non-active metals will only displace hydrogen gas and react with and will react when the solutions are acidic, so when they're reacting with HCl. And those are going to be our compounds lower on the activity series. You can also have completely non-reactive metals, which will do absolutely nothing whether they come into contact with water or acid, and that's what these ones lowest down are going to do. We also have reactions with metals. This is a single displacement reaction, which you learned about in Gen Chem 1. Solid metals will only react or displace other metals that are lower than that solid metal on the activity series. Okay, so the higher up a metal is on the activity series, the more metals it will react with, because it will react with everything underneath it. The further down a metal is, the lesser amount it has to react with. It won't react with anything above it on the activity series. So let's look at the example I have here. Zinc solid reacts with tin nitrate to give zinc nitrate in tin solid. Zinc solid is our solid metal. It will react with all of these metals. Since tin is in there, it will react with it, and this reaction will occur. If we did the opposite and we started with our zinc solid and we reacted it with, or we mixed it with zinc nitrate, since zinc is higher than tin on the activity series, it won't react and nothing will happen. Okay, so it has to, you look at where the solid metal is first, and it'll react with everything underneath it. It won't react with anything above it. Again, the more active the metal, the more it wants to exist as its ion, and the more it will react with. I'm going to jump in and go through some of the reactions that are a part of this lab and come back throughout to kind of explain what's happening. So let's jump into some of the experiments. Okay, so what I have here is a beaker, a shallow beaker filled with deionized water, and I've also put some phenolphthalein in there so we can actually see the chemical change as it happens. Right here I have a piece of elemental or solid sodium, okay? It's nice and shiny, lustrous because it's a metal. It's not as shiny as when I first cut it because it is oxidizing in the air. So I'm going to go ahead and put this right into my solution, and we're going to see what happens. When I'm reacting sodium with water, what's actually going on? Well, I'm taking sodium solid and mixing it with water, which is a liquid, and we saw that the phenolphthalein turned pink. Phenolphthalein turns pink because it's becoming a basic solution. What's a basic solution that you know that has sodium in it? Sodium hydroxide, NaOH. We also saw that a gas was released. It kind of looked like steam, and that's hydrogen gas. Okay, this is not balanced, but this is what's happening. We're taking sodium solid and reacting it with water, and we get a basic solution of NaOH, and hydrogen gas is being absorbed into the air. Okay? Next up, we have potassium. This is potassium. Again, it's just solid elemental, almost has like a purpley hue to it. And again, in my beaker, I have water and phenolphthalein so you can see the reaction. So now that we've done the reaction with potassium, the reaction that we look at as a chemical reaction is the exact same. We have potassium solid plus H2O liquid goes to potassium hydroxide plus H2. But this reaction was a more vigorous reaction. We saw that the flame popped up almost immediately, whereas with the sodium it took a little bit of time. But with the potassium it happened almost immediately, we saw a big explosion because of that potassium. So why is potassium more reactive than sodium? Well, it has to do with the electrons. Sodium and potassium are both group 1 metals. Okay, so it has one electron in its outer shell. It has one electron in its outer shell, which is an S shell, which we know likes to have groups of 2 electrons. So when it's only half filled, it's not as stable as if it was either completely filled or no electron in its valence shell at all. So these compounds want to get rid of that electron as soon and as fast as possible. Sodium is higher on the periodic table than potassium is, so its valence electron is a little bit closer to its nucleus and it's held on a little bit tighter, okay? So it will react, it takes a little bit longer to react, it takes a little longer for that electron to come off. Potassium, on the other hand, has a whole extra shell of electrons before it gets to its valence shell. So now that electron is even further away from its nucleus, and there's the magnetic pull, there's the words, the magnetic pull from that electron and its nucleus is a lot weaker than with sodium, so it's a lot easier to take that electron off, and that ends up in a very a more vigorous reaction. Okay, in my beaker I have water and phenolphthalein, and right here I have a piece of solid elemental calcium that I'm going to put into this beaker and have it react. Okay, so in each of my test tubes here, my 4 test tubes, I'm going to add a piece of metal, all different types of metal, and then I'm going to add a little bit of water. So first I have some iron, then I have some tin, then I have a piece of magnesium, and then I have some zinc. Oops. Okay, so to each of these, I'm going to add just a little bit of water. Doesn't matter how much, and I'm just gonna swirl them around a little bit, just so that all the water is getting in there and it's fully submerged. Okay, and we're just gonna let those sit for a couple of minutes. So these have been sitting for about 5 minutes, and nothing really has happened so far. There's no production of bubbles, there's no degradation of our sample. So what we're going to do is put these into a hot bath. So we're going to start these into a hot bath so that we can help the reaction move forward. And what I'm going to do is add a little bit of phenolphthalein to each of them so it can indicate when a reaction is happening. We already see one turning a little bit pink. It looks like to be the magnesium back here. So let's take a little bit of time, let these react and see what happens. Okay, let's take a look at these. So if we look at the zinc, it's kind of hard to see in the camera, but there is like a light pale pink hue, especially right around where the zinc is. Okay, it's kind of pink in that solution. Next up we have the iron, which is a very clear pale pink solution, so that had a reaction. The magnesium is very clear that it is pink and it reacted. And then finally we have the tin that has no pink to it at all, and it did not react. Now we're going to react all of those same metals that we just reacted in water. We're going to react them with 6 molar hydrochloric acid. We see the magnesium went really, really quick. It's not even in the thing anymore. And the iron and the tin didn't really do much, but the zinc is definitely reacting. So again, magnesium completely gone, completely reacted. Zinc still reacting. Tin, nothing. And iron, nothing. Okay, in this test tube I have a piece of solid copper wire. And in this one I have some pieces of zinc, little pieces of zinc, okay? Now, into the test tube with copper wire, I'm going to add a small amount of zinc nitrate. And into the test tube with zinc, I'm going to add a small amount of copper sulfate. And now we're going to wait about 5 minutes for these to start to react. Okay, so it's been about 5 minutes. If we look at our test tube that has our copper in it, nothing really changed about that copper. It's still just a clear solution and it's still just copper wire. If we look at our zinc, we notice that it has all these kind of like black pieces to it. If I shake it, I can get more of that zinc to come out, some of that shininess to come out. That shows that a precipitate formed and that we had, in fact, a precipitation or single replacement reaction happening with the zinc and the copper sulfate. Okay, so you can keep kind of knocking off some of that solid and reacting it with more and more zinc. Okay, so now we're going to start reacting with some nonmetals. So I have in my first test tube here some bromine and water. So So that's Br2, elemental bromine, and I'm going to mix it with some hexanes. I'm going to cap it nice and tight. I'm going to shake it vigorously. This is just so that all the bromine can react with and dissolve into the hexanes. Okay, so hexanes are nonpolar. Bromine in water is technically polar because of the water. So all of the bromine, which is nonpolar, reacted and went with the hexanes. And now we see that this is the bromine and this is the water. We're going to do the same thing with iodine, but now in methanol. Iodine. I'm going to add hexanes to it. Cap it, and we're going to shake it vigorously. So, because the iodine was in methanol, and which is polar, you kind of start to see the two layers forming on iodine. It may take a second for it to split, but we'll see that. Next up, I have some sodium iodide, so iodine ion, and I'm going to mix it with a little bit of bromine water. Cap it and shake it vigorously. I'm then going to add some hexanes to it so that it can form its layers. And we can compare. I'm making a mess. I'm gonna let that settle. Next, I have some sodium bromide, so bromine ion. I'm going to add my hexanes. And then I'm going to add a little bit of my iodine. We're going to cap it. Shake vigorously. So, we have a bunch of solutions here. This is bromine reacted with hexanes. This is iodine reacted with hexanes, so we see two layers. Now we can take those two layers and analyze what is where and what is now reacted with each other in both when the iodine was the ion mixed with bromine, and then when the bromine was the ion and mixed with iodine.